should know to prevent COVID-19 second wave and save lives. This is Anna Teti, Professor of Histology at the University of L'Aquila and Chair of the TMS. And I have the honor to introduce you to excellent speakers, Professor Alberto Mantovani, immunologist and Professor of General Pathology at the Humanities Research Hospital in Milan, Italy, who will talk about COVID-19 and immunity, progress and challenges, and Professor Taki Yamada, venture partner of Frazier Healthcare Partners, Menlo Park in California, USA, who will tell us about his thoughts on vaccines. So the roundtable will be chaired by Professor Nicola Petrosillo, Director of the Clinical and Research Department of Infection Diseases at the Lazzaro Spallanzani Hospital in Rome, that you know very well because he presented an excellent lecture to the TMS during the lockdown. So I hope you will enjoy the event and will contribute to what we expect will be a lively discussion. So I hand over now to Professor Petrosillo, who will introduce the speakers. And thank you very much for your attention.
Thank you, Professor Teti. Welcome to our. I wish to thank the University of L'Aquila and the people joining this important webinar with well-renowned speakers. And the title is a little ambitious. I think that predicting changes in the incidence of SARS-CoV-2 in humans requires understanding of the interaction between natural processes such as host immunity and intervention, such as physical distancing and washing masks and so on. Therefore, the study of complementary theoretical insights into the dynamics of the host-pathogen interaction is becoming very important, relevant. Intervention can be conceptualized as breaking one or more rings of the chain of infection, which in turn relate to natural processes accompanying the life cycle of the virus. The first link of the chain infection is the virus itself. The chain of infection could be interrupted at the point of the reservoir, which can include hosts and the environment. The third ring of the chain is represented by the transfer of the virus between hosts. Interrupting the transfer of viruses between hosts being the main target of control measures. The use of surgical masks reduces respiratory spread of infected droplets and the potential can minimize the spread of infection. So we should consider the portal of exit and the portal of entry of respiratory viruses as link to be broken for minimizing the spread of infection. The last link is represented by the characteristic of the susceptible host. It has been estimated that about 11% of individuals worldwide in the general population have antibodies against SARS-CoV-2, and for herd immunity, we need more people. It's been estimated more than 2/3 of the population, or less if we consider population heterogeneity. More recently, a deeper insight has been given to human genetic differences accounting for a less or more severe course of COVID-19, and to train the natural immunity of which Professor Mantovani is a great expert. So it's a great pleasure to introduce the first speaker, Professor Mantovani, which curriculum vitae is unbelievable. I just want to read that he was president of International Immunological Societies. He was head of the Department of Immunology and Cell Biology of the Istituto di Ricerche Mario Negri in Milan, Italy. He is scientific director of Istituto Clinico Humanitas, president of Fondazione Humanitas. He is full professor of general pathology, School of Medicine Humanitas in Milan, and a chair of inflammation and therapeutic innovation in London and the Queen Mary University. He has a lot of publication, more than 1,200 publications with unbelievable age index. Please, Professor Mantovani.
Good afternoon. Well, in the case of touching, it's a different time scale. But for those of you who are in Italy, all of you, good afternoon. It's a pleasure to be with you. I am going to share my screen now. Hopefully it will work. Here it is. Can you see my pointer?
Yes, we can.
Good. So I'm a medical doctor and an immunologist, and an oncologist by training, but I'm an immunologist by vocation. So this is my representation of the immune system, extremely complex. We don't know all the instruments, the repertoire, and the players in the immune system. And when I was confronted with COVID-19, and that was in February, gosh, for some reason, the presentation is stuck for some reason, and I'm sharing my screen, but, oh yes, here it is.
Could you please try to, oh, yeah. Okay, good.
Oh, now it's working. So I was confronted with SARS-CoV-2, and this is the virus as seen by three of my grandchildren. And you can clearly see the spike protein here. And this is how I felt. I went back to Greek philosophy, and that's Socrates, I know that I don't know. And it's much more what I don't know about the virus and its interaction with the immune system than what I know. And for those of you who are interested, the Accademia Nazionale dei Lincei, for touch, this is the National Academy of Science. The Accademia Nazionale dei Lincei is a document, and we have journeyed through the summer, and we are preparing the new version of it. So you can find there all I know about, all we know, and it's three of us who are responsible for that, and it's the Health Commission of Accademia Nazionale dei Lincei. So this is a summary of the story. First of all, the virus. Let me make a comment. I'm not a virologist, but of course, I have to keep track of the enemy. And in addition, some of the molecules that we identified we have been involved in studies in prime journals concerning these the interaction of molecules that we cloned or we identified and viruses or pathogens or microbial pathogens. So the virus interacts, but there is an issue about the presence and occurrence of the virus in cells of the immune system. The outcome of the interaction is dictated by viral load. Of course, we have had springtime, summertime, less, and as Nicola said, we are protecting ourselves, and people at risk, elderly people, fragile people are protecting themselves, viral load, aging, inflammation is very important for aging, lifestyle, of course, smoking, for instance, and genetics. And let me have a comment on genetics. I think we had the first study on the genetics of the human population in open access, Stefano Duga. And then we were part of a European study with colleagues in Spain, Germany, Norway, on genome-wide association of severe COVID with respiratory failure. And this is the message. Genetics is important. Chromosome 3, where some chemokines are located. And this is interesting for me because our group was one of the groups who originally described chemokines. But the jury is still out concerning blood groups. We had a report on blood groups, and the jury is still out. So this is science. Nicola and Tachi, Anna, young people, science, you are ready to question your own data. And this is the blood group. And you see it's much weaker in general. So no question about genetics, no question about chromosome 3, genes of the immune system but question mark about black group. Then the innate immune system is confronted with a virus. And there is a cellular arm, a humoral arm. We clone some of the molecules here. And of course, let me remind you that in 90% of the cases, the innate immune system takes care of our encounters with pathogens. And this is how we dissect innate immunity in this particular case with on PBMC, peripheral blood of our patients, then single cell analysis, and single cell analysis run on patients in United States and Israel. So international dimension, handling of complex data that require bioinformatics and artificial intelligence. And of course, then you have the directors of the immunological orchestra, the T cells, and you have production of antibodies. So the adaptive immune system. And of course, downstream of plasma cells and B cells, you have antibodies. And of course, we have serology. Here, for instance, is our own effort that was put in open access and now is in press in Nature Communication. We have done a relatively large, for the time, at the time, serological analysis, 4,000 subjects in our community, showing differences, and Nicole alluded to it, differences in the frequency of people positive for antibodies. And we do know, we don't know, for instance, a study that is now available in Cell by Hans Gustav Ljunggren and colleagues at Karolinska, showing that this is obviously an underestimate of the number of people who have been exposed to the virus. And we have our own data on that. And of course, this type of study is very important for the follow-up and for understanding how long does memory last. But again, the antibodies are just the tip of the iceberg of the response. Downstream of recognition by innate adaptive immunity is failure, effective of inappropriate T-cell responses, uncontrolled inflammation, late antibody appearance, and cytokine release syndrome, macrophage activation, and endothelial cell activation. And of course, we're all familiar with acute respiratory distress syndrome and all the problems. Let me just emphasize that there is a new disease called multisystem inflammatory syndrome. C stands for children, adolescents more than, children. It's a late new disease that was originally described in the UK and in Bergamo, in northern Italy. It was originally named as a Kawasaki-like syndrome. It's an inflammatory syndrome that appears after apparent resolution of the infection, So we are confronted with new scenario. And again, there is much more that we don't know than what we know, at least that I know. Let's put it this way. And well, the only, touch is going back to that, I'm sure. The only therapeutic strategy that has been proven to improve death are low-cost glucocorticoids. The original study is Hornby et al. In UK, and there are new studies, and my colleague, ICU colleague, Maurizio Cecconi, was part of this WHO effort. But the scenario is changing. Let me go back to this situation down here. Some of us were aware of the data, but the data are now available in Science. There are two studies, again, with a significant Italian contribution, because Andrea Biondi at San Gerardo Hospital, and the group at San Matteo Hospital, and then the group, I'm missing someone, there was a third group, San Raffaele Hospital. And the study was coordinated by Jean-Laurent Casanova and by Gigi Notarangelo at NIH. And I think that this changes a little bit the landscape again. Well, first of all, a substantial fraction of patients with life-threatening COVID-19 have what we now call inborn error of immunity, and in particular of type 1 interferon-mediated immunity. Inborn errors is what we used to call immunodeficiency. It's actually immunodeficiency. And in parallel, essentially the same group discovered that in another subset of patients, there are autoantibodies that block the same pathway, which turns out to be, as we may have guessed, which turns out to be essential for the first line of resistance and then activation of an appropriate adaptive immune response. So the general, I will stick out my neck and say that the general picture is that COVID-19, severe COVID-19, is located at the intersection between autoimmunity, immunodeficiency, and uncontrolled inflammation. I will not talk about vaccines. I think Tachi is going to discuss that. Let me just mention an aspect of vaccines that usually is not under the limelight, and that is pathogen agnostic protection conferred by vaccines. And this is a slide that is taken from a review that a paper that I was asked to write for New England Journal, and Mihai Nitia and myself wrote the paper. And in essence, let me remind you that when my grandchildren are vaccinated against measles, they will be protected against measles, but they will also be protected against, for instance, upper respiratory tract infection. That's the most dramatic case, but there is plenty of evidence for that, correlative evidence that BCG may do the same. And this is associated with what has now been called training, and Mihai Netea is the guy who called training. I did some of the early studies on that in vertebrates. Training of innate immunity, and of course, we cannot suggest people to get, for instance, a BCG vaccine because the prospective control studies are ongoing, so we don't have the answer. What we can say to people, I think, is that they should get their shots. For instance, in this season, they should get their shots. In the case of elderly people, flu, pneumococcus, and herpes. They should get their shots also with the idea that this is good training, good general training for their immune system. And so let me go back to philosophy. I know that I don't know, and I know and I realize when confronted with COVID-19 that nature is fond of hiding yourself, as the philosopher Heraclitus said 2,000 years ago. And this is an Italian painter, Lucio Fontana, and I think that these cuts in the painting is an invitation to go for the unknown. And once more, I look forward to the discussion.
Thank you very much, Professor Mantovani. Very, very interesting short presentation just to begin the discussion. I don't see hands. I have some questions for Professor Mantovani. You were talking about selected vaccines such as BCG or microbial component that can boost antimicrobial function in myeloid cells that are responsible for if I'm not wrong, of innate immunity, the so-called trained innate immunity. What is your opinion regarding studies that compared BCG coverage and the COVID-19 incidence worldwide?
Yeah, this is one of the strong evidence for that. I mean, there is plenty of data on that. There is one PNAS paper that we quote in the New England paper, which reports a meta-analysis of the epidemiology of BCG coverage and susceptibility to COVID-19. In terms of actual, at the end of the paper, we say we should not use BCG to prevent COVID-19, except for being part of a controlled clinical study. And there are now, our head count is 10 prospective trials aimed at assessing BCG in a prospective way. And there's actually a prospective, but I think the evidence does not allow us to make a recommendation. The only recommendation we can make, I think, is get your shots. It's good training for the immune system. Some of us feel that perhaps one of the reasons why children are relatively resistant to COVID-19 is that their immune system is trained, is subjected to regular training by the vaccination calendar. But that's, again, it's circumstantial evidence. It's not prospective clinical trial.
Yes, that's true. I know a trial by a Danish group on healthcare workers, and the aim was to reduce the days of the healthcare workers not working, mainly. Just to, that's very interesting. I don't see hands raised. Anna, if you have questions, I have one. I have a very interesting, because a group in the United States, the first author is an Italian, Grifoni, recently identified SARS-CoV-2 reactive CD4 T cells in individuals that were unexposed to COVID, suggesting cross-reactivity, T cell recognition between circulating common cold coronavirus, because coronavirus is, as you perfectly know, is a family of viruses, including a common cold. And don't you think this could be another reason for differences in the spread of infection and waves of spread of this virus in a susceptible population?
Yeah, I think the paper is very interesting, and actually two papers, and Alessandro Sette is one of the co-authors of the study. I think it's very interesting. The epidemiological evidence is not, as far as I understand, as far as I can see, does not really provide strong suggestion that if you get a common cold, that simplifies things a little bit. You have a relative protection. And I learned from tumor immunology that sometimes you can demonstrate that you have T cells that recognize tumor cells, but they are actually not really very effective. Let's put it this way. So I think it will be very important to get epidemiological evidence to show that this type of reactivity is actually relevant for resistance. But it's very interesting.
Yeah, I would like just to propose to hear Professor Yamada talk on his thoughts on vaccines, and then we can have a general discussion on both presentations.
Oh, good. Okay, thank you, Professor Mantovani. That's my great pleasure to introduce Professor Yamada. Professor Yamada is a venture partner with Fraser Healthcare Partner, and he focuses on creating companies and providing strategic guidance to existing companies. He's chairs of boards of several companies, Phathom Pharmaceutical, Passage Bio, and serves as director of Agilent Technology, and more and more. He also served as a president, a very, very important president of the Bill and Melinda Gates Foundation Global Health Program. He was also member of the board of directors of GlaxoSmithKline, and before of the chair of the Department of Internal Medicine, the physician, is a medical doctor at the Michigan Medical Center. Professor Yamada is a member of the National Academy of Medicine of the States, and has been conferred also an honorary appointment as Knight Commander of the Most Excellent Order of the British Empire, the Honorary Citizen Award from the government of Singapore, and Order of the Rising Sun, Gold and Silver Stars from the Japanese government. The talk of Professor Yamada is thoughts about vaccine. Please, Professor Yamada.
Thank you very much, Professor Petros. Can you see me okay? Can you hear me okay?
Yes.
Okay, great.
Yes.
We can hear you, but we don't see you.
Okay. Well, thank you very much, and I'm pleased to follow Professor Mantovani's excellent scientific presentation, in which he discussed much of what I was hoping to mention in my brief comments from a public health standpoint. I have to ask, where are we today? The first case of COVID-19 was reported, as you know, on December 31st of 2019. If it had been reported one day later, it would be called COVID-20, but it's called COVID-19. Amazingly enough, the first genome sequence of SARS-CoV-2 was published online and shared globally just 11 days later on January 10th, 2020. By March 11th, the disease was global and the WHO declared it to be a pandemic. And you all know today there are more than 34 million cases and greater than 1 million deaths. What is most amazing is that today we have multiple vaccines available and will likely be distributed in the first quarter of 2021. So what do we think about the vaccines, and what is behind our thinking about the vaccines? Let me discuss a few observations. First, the people who get infected do generally develop a strong antibody response. And once infected, it's rare that someone gets reinfected. So the antibody response seems to be protective, at least for a while. However, as plainly observed in many reports, sometimes the sickest patients have the highest neutralizing antibody levels. Therefore, it's clear that protection against the most severe consequences of infection seems to require more than just antibodies. A robust cellular and innate immune response seems to be necessary for that, as pointed out by Professor Mantovani. In addition, the majority of people who are exposed to the virus don't seem to get infected. And the majority of people who get infected have no or very mild symptoms. This implies that there must be some sort of widespread pre-existing protection, if not immunity. How is this possible? Well, the answer seems to vary from group to group, but here are some hypotheses. For children, it may be because they are vaccinated with the measles, mumps, and rubella vaccine. as has been observed by many, there is sequence homology between SARS-CoV-2 and the measles and mumps viruses in their fusion proteins. And there's 29% amino acid homology between the macro domains of SARS-CoV-2 and the rubella virus. Interestingly, widespread use of the measles, mumps, and rubella vaccine began in the 1960s. So people who are over the age of 60 generally not had MMR. And of course, that may be at least one reason why there is this disparity between the high mortality observed in the elderly and the relatively low mortality observed in children. One of the remarkable aspects of this pandemic is that there is a huge disparity in the deaths per million population observed between nations in Asia and nations in Western Europe or in the United States. In general, the Asian nations had a number of something less than 20 deaths per million, whereas in the US and Western Europe, the deaths per million number in the 600 to 700 per million. One possible reason for this is the widespread use of BCG in Asia. In Asia, tuberculosis was a major problem after the war, and BCG vaccine became very commonly used and mandated in most countries in Asia. And as pointed out by Professor Mantovani, BCG seems to work by training innate immunity. One of the most recent observations is a study conducted in Europe that showed that BCG vaccination resulted in a 79% reduction in respiratory of probable viral origin in the elderly. Now, this was not specifically against SARS-CoV-2, but it was against respiratory viruses of all causes. For the general population, there are coronavirus associated with the common cold, and there may be some sort of immune response to them that may provide a level of cross-protection against SARS-CoV-2. There's an interesting study in San Diego that indicated that if investigators pulled samples, random samples out of the freezer from subjects that they drew the blood from in 2016 and 17, long before SARS-CoV-2 came about, and then tested them, they noted that 50% of their samples had T cells, which cross-reacted with SARS-CoV-2. So the conclusion from all this is that there may be some sort of basic underlying non-specific immunity that may be as high as 50% of the population. And an addition of just 15 to 20% additional infections could lead to what is known as herd immunity. What are the implications of these findings with regard to the vaccines that are available? As I noted, there are at least a dozen vaccines which are likely to be available at the beginning of next year. At this point, and the rate at which people will be vaccinated, and the rate at which there is some sort of resistance to the virus, it may be that in reality the vaccines will not have much impact beyond where the disease is going today. However, there is no question that vaccines are absolutely required to restore public confidence. Now, how will that confidence be engendered? First of all, we do know that if you have a vaccine that doesn't have an impact on cellular or innate immunity, it may protect against infection, but it may not protect against the worst consequences of infection. Secondly, vaccine safety has yet to be determined. There is this phenomenon called antibody-dependent enhancement, where the disease actually gets worse with the vaccine. This has been observed most famously with RSV and most recently with dengue vaccines, and is said to have been observed with other coronavirus vaccines. In the mid-1970s, there was an outbreak of swine flu, and in the United States, at least, there was a mandated vaccination of all military personnel with this vaccine, and there was a surprisingly high number of patients with Guillain-Barré syndrome. And of course, you've heard most recently, the Oxford AstraZeneca vaccine produced a patient with transverse myelitis. The clinical studies have resumed in Europe, but in the US, the FDA has prevented the studies from continuing because they believe they have additional information that requires explanation before opening the studies up again. So there are going to be many vaccines, and they're going to be made available to the public without their safety having been tested, with their efficacy being tested only minimally, and they'll be widely distributed because of the mandate, the requirement for the public for general confidence. Then the question becomes, how do you make the vaccine available for everyone? You see, it takes a long time to make vaccines. The largest manufacturing facility in the world for making vaccines is in India, at the Serum Institute of India. This organization produces more than 60% of the world's vaccines today. And their full capacity is 60 million doses per month. That means about 700 million doses per year. And most of the vaccines require 2 doses. So those 700 doses can service about 350 million people. So just to vaccinate everybody in India will require 3 years of full manufacturing by this facility. That means they can't make vaccines for all the other diseases in the world that they make vaccines for. Now, the full manufacturing capacity of the world may be on the order of 200 million doses per month, or roughly 100 million people can get the vaccine each month. So you can imagine there is a long line waiting for this vaccine. One of the major problems in the world has been, in the past, nations who have vaccine manufacturing capacity nationalize their vaccine supply. So in other words, if a country makes a vaccine, it will not allow the exportation of the vaccine outside their country until everybody in their country has been vaccinated first. The other problem is that rich countries have co-opted the manufacturing capacity of the world. They have already pre-purchased the capacity of most of the major manufacturing sites and the manufacturing companies. It's not clear what that means. It's not clear whether they will be able to receive vaccinations from outside their country before that country has already met its supply. But it does mean that they will get it before people who haven't paid. Then there's this question of logistics and storage. You see, the Pfizer vaccine, for example, has to be stored at minus 70 degrees. You can imagine the logistics challenge of storing all the vaccines at minus 70 degrees. It usually gets distributed in dry ice. Once you open the package of dry ice, then you really have very limited number of times you can open that package. The Moderna vaccine requires minus 20 degrees. Just to monitor that any dose of vaccine has not been exposed to temperatures above the minus 70 degrees or minus 20 degrees is a challenging task in and of itself. Then there's the question of whether you store the vaccines in multi-dose vials versus pre-filled syringes. Most countries in the Western world like their vaccines in pre-filled syringes. They don't like multi-dose vials because of the potential for infection of the supply every time you break the seal of the multi-dose vial. You can imagine shipping 1 or 2 billion pre-filled syringes. It would fill 100 747 airplanes at the very least. Then the question is prioritization. Who gets the vaccine first? Is it the nations that are at greatest risk? Is it the primary healthcare workers in those countries? Is it the elderly? Is it the school children? These decisions have not been made, and there will be tremendous contentiousness when everybody understands that there is very limited supply, even if the vaccine is launched in the first quarter of next year. We do not yet have the infrastructure or the operating principles to make this kind of mass vaccination simple, intelligent, and successful. And that is our biggest challenge. Thank you.
Thank you very much, Professor Yamada. Now we have the questions. We already asked several questions to Professor Mantovani, but I see that there are some questions, and I ask Professor Teddy to help me. I have a question for Professor Yamada, that is, how long will immunity caused by the vaccine will last? I mean, natural and cellular immunity, in your opinion?
Yeah, we have no information at this point. We have no understanding of this. And generally, when a vaccine is released under normal circumstances, there is at least data to suggest 1 or 2 years of coverage. We have no idea at this point how long the immunization will last. And we don't yet have a correlate of protection. We don't know that there is a certain level of antibodies that will provide protection or not. And whether cellular immunity has to be present to provide protection. So we're moving so quickly that at this point we have no idea of how long the immunity will last and what the correlates of protection will be, even if we have levels of antibody that will persist. But right now, the natural infection produces an antibody response that is relatively short-lived. It looks like about 6 months, or after 6 months, quite a bit of the antibody response is reduced.
Thank you, Professor. Professor Mantovani, you raised your hand.
Yeah, a fantastic talk, and I have a vested interest. What about, you mentioned elderly people and fragile people. Are we going to get, and of course that would be a priority, I guess, after healthcare workers, for frontline people. Are we going to get a minimum of information about response? I mean, we know that in flu we get, and of course we lose repertoire, we lose memory, immunological memory, I mean. Do you have a sense about that?
Yeah, you know, the thing is, it's a brand new game here, because in the case of flu, antibody levels are a good correlate of protection. In this case, we do not know. And we will not know because the vaccine will be rushed out there so quickly. So it's going to be kind of like the wild, wild west. We're going to be vaccinating a lot of people. We'll be gathering data as we vaccinate people. You know, the big question is how much protection will they be for the elderly as opposed to the young? You know, at least the antibody levels with most of the vaccines seems to be similar for the elderly as for the young people, but that doesn't mean protection per se, because protection in the elderly may require much more. And so, and the other part of it is that although this virus is mutating at maybe half the rate as influenza, it is still mutating. So we don't know after vaccination what is the frequency with which you will have to be vaccinated again with a different strain as we have to vaccinate ourselves every year with influenza in order to cover the strains. So these are all questions that we wish we had the time to answer before launching the vaccine. But both public and political pressure are forcing us to move quickly with a vaccine into the marketplace before any of these questions can be answered.
There are several questions in the chat. So there are many, so maybe we can have short answers. Can you hear me?
Yes.
Okay, yeah. So from Vincenzo Flati, Prof. Mantovani, yesterday evening on TV, you said that Mr. Trump was treated with the monoclonal antibodies that are not proven to work. So on what basis Mr. Trump was treated with those antibodies?
Well, it's compassionate use. It's what is defined compassionate use. Let me summarize the situation concerning treatment with antibodies. First of all, it's in the roots of immunology to use the plasma from people who recover to treat patients. So there is plenty of evidence and widespread use. There has been plenty of usage of hyperimmune plasma also in this country. And there are three, unfortunately, there are three controlled trials with negative results. And one was run in the Netherlands, one was run in China, 100 patients didn't achieve the prospective 200 patients, and one was run in India. Then there are monoclonal antibodies. To the best of my knowledge, there are data. I haven't seen the actual data, but they say there are data from phase 2, which are encouraging. But again, we do not have evidence. Have an echo in my. I mean, there is no evidence from a control trial. My bias is that antibodies are going to help. We use them for treatment of cancer, some infectious diseases, autoimmunity, and more. And so, but you have to find, or we will have to find the right window for usage of antibody, as we did for glucocorticoids. I mean, there's a method, low cost. I mean, initially there was an official recommendation by WHO, and there was an official recommendation in China not to use glucocorticoids. And then the empirical usage, for instance, in my institution, and the clinical trials, again, we were involved in some of that, showed that if you use them in the appropriate window, then they can help. So that's, going back to your question, that was labeled as compassionate usage.
Okay,
thank you, Professor Mantovani.
Yes, go ahead.
Sorry, sorry, Anna. There are two person asking that raised the Antonio Maurizi. Antonio Maurizi, please, Antonio.
Hello. First of all, congratulations to all the speakers and the chair. Very, very nice events. So I have a question that can be addressed by both Professor Yamada and Professor Mantovani. And I was thinking, so in the past we had other outbreaks like the SARS in the 2002 and the MERS. But why the COVID-19 virus spread worldwide so fast, so compared to this other virus that we had. It is possible that there is things related to genetics or population or whatever.
If I could answer that, the first case of SARS-CoV-2 seems to be dated to November 17th, although the first report came December 31st. During that 6 weeks, you can imagine all the air travel throughout the world, from anywhere, and effectively, the way that you try to deal with a pandemic is initially containment, but by the time it spread all over the world, containment was too late. It was not possible to contain it. And then there was very much a delay in reporting, not just in China, but everywhere else in the world, so that
There's a problem. The microphone of Professor
There is
Yamada.
problem here.
Please unmute Marco. Could you help us unmute?
Professor Yamada, I think you accidentally muted yourself. Could you?
Oh.
Okay, there we go.
Okay.
is that all right?
Yeah.
No, it's again mute. It's again mute.
Oh, you muted yourself again, or someone is muting you?
Someone keeps on muting me, I think. Can you hear me okay?
Yes.
Okay, so what I was saying is that but 3 months after the first case, November 17th, reported December 31st, and March 11th is declared a pandemic. By then, it's everywhere. It's in every community. It's spread so far and so fast that there's nothing you can do about containment. Then it requires some very drastic measures, which many communities were unprepared to implement immediately. So this is unfortunately a case of rapid transit and very slow communication.
Can I add something on top of that related to Northern Italy? Because and we now have a picture. It's coming out in Nature. I mean, it's in open access, but it's coming out in Nature communication with an analysis of 350 isolates of the virus in the Lombardy region, and the picture is very clear now. We had 2 tsunamis in Northern Italy. Both the virus entered at least twice independently in Codogno, so the south part of Lombardy region, and in the Bergamo area. On both cases, the isolates show that the viruses virus was coming from Northern Europe, possibly Germany, because of the commercial very strong relationship we have with Germany. And what actually, and the main author is Carlo Federico Perno, so Nicola knows him, a virologist, a very good virologist. And what happened is that for a month and a half, and we can track back based on antibody occurrence of antibodies in blood donations. So we had 2 tsunamis in the Lombardy region and northern part of Emilia, in a sea of tempest because of the seasonal flu and seasonal pulmonary infection. For more than 1 month, 1 month and a half, the virus ran all around in these areas. And this is why we had such a disaster. I mean, so it's just, I'm translating to Italy what Professor Yamada said at a global level.
Anna. Anna? Okay. Alessio Cortellini, please. You raise your hand. Alessio? Do you want to ask a question?
It was a mistake. Sorry.
Okay, maybe I can read something from the chat. Let's see.
Somebody turned off his microphone.
So we have Loredana here, say very interesting. Different SARS-CoV viral strains have been isolated so far, and phylogenetic studies show that they may all be coming from a first common strain. While the virus mutated further, passing on from one host to another, did its characteristics change? Sorry. Okay, its characteristics change, so it became more or less virulent.
Professor Mantovani probably knows much better than me, but as I understand it, the mutations observed thus far have not made it more virulent, but possibly more easily spread.
Well, I'm not a virologist. I'm an immunologist. But as I said, I have to follow what, and there has been a lot of debate in this country, and Nicole and I were commenting on this earlier. And there has been confusion between the pathogen and the disease. And since there are students, I think we should clarify that. The pathogen mutates, and there has been to the best of my knowledge, there are 2 papers in Cell, 1 paper in the Lancet, and then this upcoming paper from Northern Italy. And in essence, there was a mutation 614 for, I mean, there may be biologists, the PhD students, 614 GD mutation, and it may have made the virus worse, but it's not 100% sure. Then there was a loss of an open reading frame, again in China, and then a few cases in Singapore, and that's the Lancet paper, but just about 10 papers. And then another paper reported mutations possibly in vitro modes in both directions. Then the disease is much less severe now, but the disease is less severe because we have had springtime, summertime, and Nicola knows much better than me than that in springtime and summertime, upper respiratory tract pneumonitis, even coronavirus pneumonitis get much better. Then we behave ourselves. I mean, we protect ourselves. We protect the fragile people. We make the diagnosis much earlier. We do early diagnosis. We treat earlier. So the people who get infected are younger, and as was emphasized by Professor Yamada, younger people are more resistant. So the pathogen has not become kinder to us. The disease is less severe because for other reasons. And if there are medical students or PhD students, don't mix up the pathogen with the disease. There are 2 different things.
And we give more steroids, and we give anticoagulants, and we care better these patients. This is true.
Okay.
Anna.
Yes, another question from Mauro Bologna. Can a cocktail of human monoclonals reach a satisfactory anti-COVID-19 complications effect? Who can answer? No answer to this question. So a cocktail of human monoclonals?
Yeah. There is data from Generon now that shows that if given early, it can reduce the number of days of symptoms, as with most of these treatments. We don't know, this is a phase 2 study, so we don't know conclusively what it will show, but I suspect that the monoclonal antibodies will prevent infection and may lower viral load early, if given early, but if given late in the disease, the immune systems that have been activated will be such that it will have a hard time preventing the worst outcomes of the illness if given late.
So Nicola, is there anyone who raised the hand?
I don't think so. I just see Marco. Marco, do you want to? Marco.
Yes, thank you. Thank you both for your amazing talks, really top level. I have a question for Professor Yamada. I guess it would be easier to produce genetic vaccines for COVID-19. Do you think that would be the way the world should go if we find a good genetic vaccine to produce enough vaccine for everyone in a short enough amount of time?
You're talking about like the RNA vaccines?
Yeah. Yes.
Yeah. There's no question the RNA vaccines were very quick and have at least in the initial clinical trials shown that they can elevate antibodies levels. What's not clear is whether they'll provide protection, because there is not yet a good correlate of protection. So we'll find out when this happens. I do know that Moderna produced an influenza vaccine that produced a high antibody level but didn't protect. So in the case of influenza, their vaccine didn't work. They also had a dengue vaccine that didn't look like it worked either. So we're the world is a guinea pig here. We don't know what's going to happen. There is no question that the mRNA vaccines will elevate neutralizing antibody levels. Whether they will provide protection will have to be determined by clinical outcomes, which we won't know for a while.
I have a question here from Katie Stoker. It's a long question, but she asked, how can a virus with a pandemic causing potential be quickly identified and distinguished compared to other novel illnesses? Who wants to reply? Alberto, you want to say something?
What was the question again?
Is how can a virus with a pandemic causing potential be quickly identified and distinguished compared to other novel illnesses? So how do we know that it is a dangerous virus?
Yeah.
Just a matter of getting people healed, or is there another way?
I can just give you some, this is very difficult research to do. And there is a scientist who has a joint appointment at the University of Wisconsin and the University of Tokyo, who is studying exactly this question when it came to influenza viruses. And he was publishing the results of his research, and there became a large outcry as to whether that research should be published because of the potential that the information contained could be weaponized by countries. So if you do research and you do small mutations in a known virus to identify how to make the virus more virulent or less virulent, there is a real danger that that can be used for unethical purposes. And that created a scientific crisis of substantial magnitude. The National Academy of Medicine had to weigh in to allow this person to publish the information. But it is a very difficult thing to do. For example, we now know coronavirus can cause this problem. Who's going to do research to determine which mutations makes it more virulent so it kills more people? Or how do we make it less virulent? That requires multi-mutation research, which can itself be dangerous. And that's the complexity of the question you're asking.
Another question is from Chiara Puri. In your opinion, will we be able to eradicate SARS-CoV-2, or is it more likely that we will have to learn to live with it? So probably it's philosophy, but maybe you can compare with the previous pandemics. I think that more or less they all were over after a while.
Sorry,
Shall I comment in the meanwhile?
Sure, yes.
Yeah, well, first of all, we should not forget that, I mean, with vaccines, we can get rid of, we did get rid of smallpox. And as of 2 weeks ago, Africa was declared free of polio. And the world could be free of polio. And we could eradicate measles with vaccines, because it's only transmitted from man to man. So that's a precondition. I don't know what will happen with COVID-19, whether we will live with COVID-19 or whether there will be an extremely effective vaccines that may allow the eradication of COVID-19, or whether the virus will mutate. So I really don't have an answer. So I would, and if I may comment in general, we may need more than a vaccine. I mean, for polio we have 2 vaccines, complementary vaccines, and we may need more than a vaccine to deal with COVID-19.
Is it a bad idea to use the measles vaccine to help also adults to combat the virus? So it's just a problem of training and not a problem of specificity against the coronavirus?
If the question is to me, I think that the best
if we can use the measles vaccine to help adults to combat the virus, so it's just because in kids there is this training that you were describing.
Actually, as far as measles is concerned, measles, and this is relatively recent evidence coming from small communities in Northern Europe that don't take the measles vaccine and then got infected. And there were material to investigate the immune system. One of the reasons why measles cause you have 20% to get, at least 20% to get infections, other infections, is that measles wipes out immunological memory. Actually, there has been a debate as to whether people, I hear an echo, and other words, I hope you hear.
Someone has
the main reason for the pathogen agnostic function of the measles vaccine, as far as I can see, has to do with immunosuppression of adaptive immunity and wiping out of immunological memory to an extent greater than we believe by measles, rather than training. I hear a noise, and I don't know whether you understand. You can hear me.
Well, I could hear, despite the noise. Yes, I could hear.
There was a Science Immunology paper describing this profound immunosuppression and wiping out of B-cell immunological memory by measles.
May I ask both to Professor Yamada and Professor Mantovani a question regarding the very next use of the vaccine against the flu if there will be any interaction in terms of immuno response or some other concern with the use of or benefit with the use of both vaccines in the next winter.
I'm not sure I understand the question. I do think everybody will be vaccinated, and it's important to do so. But the number of people that can be vaccinated is very restricted. So, as I mentioned, the total global supply of vaccine may be 200 million doses per month. And that means if people need 2 doses of the vaccine to be fully vaccinated, then only 100 million people can be vaccinated each month. So if you consider the number of people in the world, 6 billion, what percentage can be vaccinated in the first year? It's a very small percentage, unfortunately. But everybody should be vaccinated.
I agree on this comment because they are saying that we should be vaccinated, but then what is the capacity to provide vaccine for 7 billion and more people? So I think that this is really impossible. Yeah. Okay, so
I'm sorry, but
can I comment on
that I'm going to have to sign off for, but thank you very much for allowing me to be a participant in this symposium.
Okay, thank you very much.
Anna, shall I comment on flu?
Sure, yes, go ahead.
Yeah, I mean, people should not forget that, again, there is limited production capacity. I mean, Nicola may correct me. I think we used to have a coverage in our population about 15%, healthcare workers about 30%, right? 3 out of 10, more or less. Now we would like to vaccinate many more people. And the flu vaccine is made in fertilized eggs. 90% of it is made in fertilized eggs. So there is a limited capacity, and as to the best of my knowledge, there is only one facility that makes a cellular vaccine. Cellular vaccine meaning vaccine produced in eukaryotic cells. And so you have to think that you have to have manufacturing facilities. You need to have the hands that prepare the eggs, and then the fertilized eggs, and then prepare. And I'm sorry, I forgot to say, as far as I remember, it's 1 egg, 1 dose of vaccine. So you can imagine the strain. So I think that the challenge that, I mean, of course, the administration, the politicians, the regional and national, they have to work it out. But in general, we have a challenge of making very good use of the vaccine that we have. That no vaccine dose goes lost.
I agree. I fully agree with you. So it's they are telling us things that probably cannot be realized. Okay, so Nicola, any other questions in the chat that are questions that are more or less what we already asked? Otherwise, we can.
I think that there are more questions, but I don't know if we have time enough to reply to everybody. I don't know how much time we have left.
Well, we are over time already. I mean, if there is anything really different from what has been asked, but I don't see. So they are more or less around the same topic. Yeah. I don't know if, Nicola, you have a specific question for Alberto, if you want to say something more.
No, I don't have a specific question. I just wanted to thank Professor Yamada that left because another commitment, and Professor Mantovani because the talk was very, very interesting, but also the chat was unbelievable because we had a lot of questions and a lot of interesting replies. I wish to thank you, Anna, for your kind hospitality, and thank to Marco Ponsetti for his help in this webinar. So please, Anna, to you.
Thank you very much. It's been really a pleasure and an honor to have you this evening with us. And I'm very happy that the young students here can understand what science is and the enthusiasm that there is around the science. I think that this is really very, very important. And they have to in some way learn to be some way. I mean, it's important that we criticize also our colleagues, also ourselves, because science is not perfect, but with some method and some rigorous attitude, I think that we can go on, and maybe in the future, in the near future, we will, win our battle against the COVID-19, ready for another battle, because of course other virus will come. So thanks a lot. And for the young students here, so these are outstanding scientists, and maybe you don't know what they do, but you should tend to do what they do, actually. So it's a way to to be attracted by science, and everybody has a mentor that we followed what the mentor was doing, and this is why we are in science, and we learned how to deal with these important and very difficult studies. So thank you very much, and I hope
the last,
go ahead.
The last is to activate. Each one will activate his or her camera, because Marco will take a picture of all the people. Please activate your camera. Everybody.
Don't be shy.
Yes, just click.
Please.
Just a click, nothing else.
Davide, Mauro, Antonio, please. Mauro Bologna, Davide Di Febbo, Antonio Maurizio. I see all in the screen. I don't know how many. Thank you, Mauro.
Sì, infatti.
Okay, so Antonio, Eleonora, Cristiano. So just to switch on the camera and smile.
Please.
Okay, Marco, go ahead.
Okay, done. Thank you very much.
Okay, thank you very much, and I hope that we can do another beautiful TMS with you and other outstanding scientists. So thanks a lot. Bye-bye.
Grazie, saluto a tutti.
Grazie a te, Alberto, grazie tantissimo, grazie Nicola. Ciao ciao.